Hi, I'm Jake Mannix, Search Relevance Architect, and I'm here with Ashish Srinivasa, Senior Data Scientist with me here at Salesforce. And welcome to our Activate session on ml4ir, a new deep learning library for search, which the Search Relevance team at Salesforce has been building since the beginning of the year, following an open source from the start approach that was encouraged by our open source programs office, and we've been using it continuously in production since it's been progressing. Ashish and I hope you find it as exciting as we do. The format of this session will be a short introduction by myself, after which I'll get out of the way and let Ashish describe in a little more detail what training information retrieval focused ML models looks like in general, and then specifically how it's formulated in ml4ir. And then we'll jump right in and give you a demo of training a learning to rank model with a notebook you can follow along with, including some pointers on where you can customize it to suit your own particular needs. We'll close out with a look at the future of where ml4ir is going in the near term, and a plea for you to join us in this journey. It is open source after all. So let's begin by trying to motivate why we started this project and touch on why current libraries and toolkits didn't quite fit the bill. Then give a little outline of the project's philosophy, structure, and specific goals, which will hopefully give you a good idea of why ml4ir might be right for your team. Search is a complex space with a lot of different types of problems, from query and document understanding, personalization, and a variety of aspects of natural language processing, all in addition to the question of ranking and re-ranking of search results. When we looked around for a library which straddled the space of allowing deep customizability, being specifically built for search, but general enough for 95% of all search problems, works out of the box without much or even zero code, while suitable for production in a JVM heavy environment, and easy to prototype with, we kind of came up short. We wanted something like Lucene and Solr for the search engine core, so we created ml4ir, which is a business-friendly, Apache-licensed, open-source deep learning library for search. What is ml4ir? It's built on Python 3, TensorFlow 2.x for the training side, and has a bunch of helper utilities written in Scala for doing JVM inference. Side note, having one project do both Python and JVM code means we have tests to verify nothing weird happens when you try to train a model with TensorFlow 2.x in Python and then serve it in TF Java 1.15. This was a big worry for us in the beginning. It's designed based on modular subcomponents like query classification, learning to rank, or whole page relevance, top result prediction, with some cross-cutting concerns like query text embeddings, metrics, and efficient common data pipelines. Lastly, one really important concept we're baking into the core of the library is sharing subslices of the models to support shared feature processing, layers, weights, in fact, full transfer learning among IR models. And with that high level view, I'll turn it over to Ashish to dig into the details and give you a tour.
Let us now get into some of the design details of ml4ir. We will look into the ml4ir data pipeline, which is built on top of TFRecords. Then we will look at how one can train models on ml4ir using configuration files alone. Alternatively, we will also look into how one can customize ml4ir for your own needs. Lastly, we will see how to save and serve the models you train on ml4ir in a JVM environment. Firstly, to understand ml4ir's data pipeline, we need to understand what the search ML data typically looks like. Here, you see two examples. The first is from a query classification task, where the goal is to classify a user query using the actual query text, given the context of the query. In the table, you can observe that each row corresponds to a single query and contains the accompanying features, the domain name, the previous products that the user reviewed, and the goal for each query is to predict the product group that the user is searching for, given their current context. What I want you to observe is that all the information needed to classify a query is contained in a single row of this table. Now, let's look at the second example. Here, the data is for a learning to rank or ranking task. The goal here is to find the best ordering of the documents for a given query. If you look closely, what you will realize is that each row in the second table corresponds to a single query document pair. Here, for each query document pair, we have the query text, the record text, and the rank of the record as seen by the user. Then there are a few numeric features like popularity, page view scores. Lastly, there is a categorical feature called the domain name, which captures the domain from which the query was made. Finally, we have a click or no click binary label. One can treat this as a binary classification problem where we try to learn for each document the probability of it being clicked and then reorder accordingly. But if we want to understand cross-document interactions and design more complex group-wise ranking functions or list-wise losses, like the best ranking models of today, we need to look at a query and all of its documents as one single whole. In the current representation, this is really difficult to do as it would require expensive group-by operations in the TensorFlow graph or in the data loaders. Secondly, we can also observe that storing this data in raw CSVs has a lot of redundant information that is common across all documents for a given query, like query text and the domain range in this example. With these considerations, we chose TFRecords to build the ml4ir data pipeline on. So what is TFRecord? TFRecord is a TensorFlow recommended data format for storing a list of binary records as protocol buffers. Protocol buffers are cross-platform and cross-language serialization format designed to store structured data. And since most search ML data is structured collection of features, protocol buffers and thereby TFRecords prove to be very effective for storage. Secondly, as TFRecords are cross-language, we can use the same data storage format in both Python and Java. TFRecords also play well with TensorFlow's data pipeline and are optimized for scale, with batching and lazy loading handled out of the box. TFRecords provide two types of protobuf messages for storing data. The first one that you see on the left is called an example message. Here, we're using it to store the query classification data that we saw in the previous slide. Each example TFRecord message contains the features for a single query as key value pairs. So the query text, domain name, previous products for a given query are stored in one single structure along with the product group, which is the classification label. We can build and store a TFRecord dataset as a collection of such example messages. The second type of protobuf message supported by TFRecords is called sequence example. Sequence example contains two subtypes of features called as context features and sequence features or features lists. We use this to store data from models like learning to rank. We use the context features to store features that are common across the query, such as query text, domain name, and user ID. And similar to the example message, this is stored as one single substructure as key value pairs. Next, we have the sequence features, which we use to store values for each feature as an ordered sequence corresponding to the documents. Here, we can see the features that are unique to each document, such as popularity score, page views, record text, and so on. Finally, since the click is also defined at a document level, we store that as a sequence feature as well. Storing the ranking data this way helps us achieve two things. Firstly, we now have a compact structured representation of data for ranking without redundant information, as the query level features are stored only once per query as context features. Secondly, and more importantly, we now have a single object that contains all the query document features for a given query. This means that we have all the information needed to learn complex ranking functions and list-wise losses for a given query without the need for any in-graph operations or any changes in the data loader. This allows the storage to be efficient and the training process to be fast. Lastly, TFRecords also play well with Spark with the help of Spark TensorFlow connector, and thus make it easier to write TFRecords from any upstream pre-processing jobs that you might have. And if you're worried about how to convert your CSV or libsvm data into TFRecords, ml4ir already provides utilities and data loaders that will do the trick for you. So now that we have the data pipeline ironed out, let's see how we can define the input features for our TensorFlow model. Defining the features for an ml4ir model is through a YAML configuration file called the feature config. Using the feature config, you can easily define the list of features that should be loaded for model training. For each feature, you can define its graph node name, data type, and shape. ml4ir also provides support for using certain features as metadata features. These are features that are not used for training, but can be used for computing custom losses and metrics. The feature config also provides support for defining the pre-processing functions to be applied on loading. These pre-processing functions come packaged within ml4ir, but custom functions can be easily defined and added to ml4ir. The pre-processing functions work on the TFRecord dataset and can be extended to support TFX or TensorFlow transform for pre-processing at scale. In the example you see on the left, we define a feature configuration for a numeric feature called page view score. Here, we tell ml4ir to convert the feature to a shifted natural log in the pre-processing step when the dataset is created. In the feature config, you can also define in-graph feature transformations on the input features. These feature transforms are part of the TensorFlow ml4ir model and form a feature layer on top of the input nodes. As earlier, ml4ir comes pre-packaged with common search-based feature transformation functions, but new feature transforms can be easily added as needed. In the second example, you see on the right, we define a feature configuration for a textual feature called domain name. This is a categorical feature, and thus we tell ml4ir to learn a categorical embedding using a vocabulary file. We additionally provide the path to the vocabulary file and the size of the embedding to be learned. The feature config also serves as a contract of handoff between the training and inference frameworks. ml4ir allows defining of serving time information like the name of feature in the production feature store or your Solr index. This can be extended to have tighter coupling between the models trained and served using ml4ir. All right, now let's see how we can define a relevance model by combining all the subcomponents. Let's do this bottom up. Firstly, you define an interaction model, which uses the feature config to transform input features into a dense numeric representation that can be used for scoring. For example, we use this layer to convert categorical features into embeddings or encode sequence features like text or any other feature transformation that you see necessary on the inputs. So once we have this, we use a model config to define a scoring function. The model config is also a YAML file, which allows one to define the different TensorFlow layers and operations that should be applied to the dense feature representation. The model config can be a simple multi-layer perceptron or much more complex depending on how you define it. We combine the model configuration with the final activation layers and the loss function to define an end-to-end scoring function called the scorer. Lastly, we combine the scorer with the relevant callbacks, a gradient optimizer, and evaluation metrics to define a relevance model. The relevance model thus defined can be used using fit, predict, evaluate, save, and load, similar to a high-level Keras API. The most important aspect of this design is that each of these blocks can be heavily customized as you see fit. This means that one can easily define custom loss functions, track complex evaluation metrics that are specific to your organization easily by overriding these individual blocks. Now, once you have defined a relevance model, trained it, and evaluated it, you want to save it and ship it to production, where it will be used to run inference. So now let's see how you save these models and serve them. ml4ir saves the models trained using the saved model format. The saved model format allows to define custom serving signatures, which are additional pre- and post-processing wrappers around the TensorFlow Keras model. This entire model can then be saved as a bundle and used for inference. The entire serving signature can be fully serialized and loaded back as a TensorFlow graph, and thus is highly performant as it can be served as a GPU-compatible code. Saving the models in this way also allows ml4ir to package any necessary feature processing that might be useful at inference time. More importantly, it provides a way to have a single source of truth for feature processing at both the training and inference time, allowing us to tackle offline-online feature drift. ml4ir uses serving signatures to also embed TFRecord parsing logic in the pre-processing step, allowing models to be served on TFRecord protobuf messages in production. This again helps in consolidating the data format used at training and inference. The feature config is coupled with this saved model bundle to determine the inference logic to pass the right features from any production feature store or your Solr index into the model. ml4ir also comes packaged with the necessary serving logic required to serve these models in a JVM-based production environment. And the JVM package provides APIs for converting feature maps to TFRecord protobuf messages, which can then be passed into the model itself to get the scores. Now that we have learned the different components of ml4ir, let us quickly see hands-on how one would go about using ml4ir for training and serving learning-to-rank models at scale. Okay, so we're going to use a Jupyter notebook to walk you through this, the demo. And in this notebook, we are hoping to train a learning-to-rank model. But more importantly, we want to walk you through how you would go about installing and setting up ml4ir and start using it as a script and a library. And you would be, in the notebook, we'll walk you through how you would define a ranking pipeline. And we will also show you an example of how you would do transfer learning by sharing weights across different models trained on ml4ir. Finally, we will see how we can serve these models in a JVM environment. For this example, we're going to use a pointwise ranking function for our learning to rank task, coupled with a listwise loss. These will be used to predict ranking scores for each query document pair, and then converted into the right optimal ordering for each of documents for each query. Firstly, let's install ml4ir. And once you have ml4ir installed, let's take a look at what the data looks like. So I have a dummy sample data set that I've created for the sake of the demo. And it's very similar to the data set that I showed you earlier on the slide deck. And since I'm loading a CSV file here, you can see that each row represents one query document pair, where the query, rank, and a bunch of features, both textual and numeric. And finally, you can see the binary click or no click labels. Once we've taken a look at the data and decided what features we want to use in the model, let's go ahead and define a YAML feature config. So in this particular example, we have two text features, query text and domain name, and three numeric features, the text, match, page views, and quality score. For the query text, we want to use it, we want to create character embeddings on top of the query text and then pass it through a BioLSTM layer so that we get the encoding. And for the domain name, which is a categorical feature, we want to use a vocabulary lookup table to convert the domain name into an ID, which can then be used to fetch categorical embeddings. The rest of the numeric features we're going to use as floating point features. Now that we've defined a feature config, let's also go ahead and define a model config. So a model config is just a simple YAML file with the different layers that you want in the actual dense neural network. And in this example, I'm using a bunch of dense layers coupled with dropout in between and ReLU activation layers. And finally, we have the last dense layer. So now that we have a feature config and model config defined, how would you go about using this in ml4ir? So if you have ml4ir cloned and you want to use it as just a script without having to write any code, then we have a ranking pipeline defined for you, which you can just call and pass it the right feature config and the model config, and point it to a directory containing CSV files for this particular example, and tell ml4ir to use CSV format, and you can quickly train ranking models. Keep in mind that ml4ir internally handles conversion of the CSV format into TFRecords, and it's optimized out of the box. So you don't have to really worry about it. So what happens when once you kick off a model training run is it's going to load the feature config and parse it and try to see what features it wants to use for training, and convert all the CSV files into TFRecords, and then load it up back to create a TFRecord data set. Then we have the model config loaded and the model defined. So you can see the different layers being defined in the model. So there's a bidirectional layer, which is the LSTM that we are using. There is also the query character embeddings that we define, and also the categorical embedding of the domain name. And finally, once you've loaded all the layers, you finally have about 200,000 parameters, and you can start training your model. So your model is getting trained with all the callbacks plugged in for model checkpointing and early stopping. And once you have that, once the model is trained, it's going to save the model, and it's going to compute some metrics and save the metrics to a file, and also write the predictions to a file. So all that is great if you don't want to write any code. But if you want to run ml4ir as a library, the way you would do it is similar to what I talked about in the slide deck. But we're going to walk you through how we would do it in code. Firstly, some setup, trying to instantiate some paths, set up directories, load, and setting up all the Python imports. Once that is done, let's load up the feature config. Since we've already defined a feature config, let's load it up and see what are the features that are being used for training. Like we defined earlier, there are 5 features which we're using for training. And once we have the feature config loaded, we can start loading the loading a relevance data set by pointing it to the right data directory, and then telling ml4ir to use the CSV data format, and by passing in a feature config. Once we have a relevance data set created, we start our building our model by defining an interaction model. The interaction model, like I previously explained, is the layer that connects, that converts the input nodes into a dense numeric representation by applying feature transformations. ml4ir already comes pre-packaged with all the feature transformations that we want for this exercise. But if you want to define custom pre-processing functions, you can easily do so and pass it to ml4ir as a key value pairs. Once we have the interaction model defined, let's go ahead and define the losses, metrics, and optimizer we want to use. For this exercise, I'm using a predefined list net loss, which is a popular learning to rank list-wise loss. And the metrics that I'm going to use for this exercise are mean reciprocal rank and average click rank. And I'm going to use an random optimizer to optimize the model. Once we have that, let's put it all together to define a scorer and combine the scorer with the metrics and the optimizer to define a ranking model. So now you should be seeing the similar model that we had earlier when we tried to run ml4ir as a script. So you'll be seeing the query character embeddings. You'll see the categorical embeddings on domain name, and so on. And you can see the bunch of dense layers that we define. Dropout, and totally 200,000 parameters again. The next step is to train your model. Once you train your model, you can also tell ml4ir to monitor a particular metric. So here I'm telling ml4ir to monitor for MRR, and it's going to use this metric for model checkpointing and early stopping and being intelligent about the way it trains. Once you have your model trained for how many ever epoch you tell ml4ir to, you can run predictions on ml4ir. Here I have an example where I'm passing in a test data set to ml4ir's predict function, and I'm sampling a few query document pairs. And you can see that for each query document pair, ml4ir has generated the ranking score, and which is converted also into the new ranking for each query. Once we have tested our models, we're happy with it. We're going to save the model using ranking model.save. And here, the key thing to note is that you can package in additional pre-processing functions that you want to be used at inference time. This is going to be packaged into the serving signature of the saved model and can be and will be part of the TensorFlow graph and can be used as GPU code in the inference at inference. All right, so that was one end-to-end flow. Now let's see how we can use ml4ir to do some transfer learning. So I've trained a model previously for query classification, and that model also was built on query text, and we learned character embeddings on it. What if I want to use those character embeddings in my learning to rank model? So that's super easy to do. The first thing we need to look at to do that is, what does ml4ir save? So when ml4ir saves a model, it saves the two serving signatures, the default serving signature and the TFRecord serving signature. But then it also saves each of the individual weights for the layers as separate NumPy arrays. So when you want to do transfer learning by loading embedding from a previously trained model, it's very simple to do. So when you define your ranking model, you tell ml4ir to load up the weights for a particular layer using by pointing it to a path. So now we have defined a new ranking model where the character embeddings are being loaded from a previously trained query classification model. And in this example, I'm also freezing the weights so that I don't relearn it. But you can also fine tune it for your new ranking data set. And here you can see the weights that we have loaded up. These are the query classification character embedding weights that I'm using with the learning to rank model now. Lastly, let's also look at how we are going to serve these models that we've trained and saved with ml4ir. So once you have a TFRecord saved model bundle, ml4ir comes pre-packaged with utilities that you would need to serve that model. Firstly, like we mentioned, we use the feature config, the same feature config that was used at training time to define what features that need to be passed into ml4ir. Next, we define a sequence example builder, which converts the input features into sequence example protobufs that can then be passed into the model. Next, we load up the ranking model itself as a saved model bundle by pointing it to the model path on this. For this particular example, I'm loading up my features from a CSV file. So I have a CSV loader, but you can do the same using any feature store that you might have, or if you want to fetch your features from Solr, that is supported as well. So once we have these features as raw Java objects, the next step to do is convert them into sequence examples. So we use the sequence example builder utility to convert these documents into sequence examples. And then the only step remaining is to pass it to the ranking model itself and then get the ranking scores for each query document. Let's see this in action. So I'm running that that function to show you what it looks like. So we have the input features as a Java object. Here you can see that there's domain name, the query text, the domain ID, there's text match score, bunch of values, page view scores for each query document. And ml4ir converts these raw Java objects into protobuf messages, which is a sequence example. So here you can see that there are context features like query text, domain name, domain ID, and also sequence features or feature lists like text match score, name match, quality score, page view score, and so on. So once we pass these into the model itself, what we get is we get a ranking score for each of the 6 documents that we passed in. And we can use these, we can sort these scores in descending order to get the optimal ordering for this particular query. Our grand vision for ml4ir is to use it as to create a search model ecosystem so that we can train tightly coupled search models. So one of the main challenges that we have in search is that we have query classification models, autocomplete models, and then a bunch of multiple ranking models, the L1, L2, L3, and so on. And we have the ranking models further talking to a top result model. One of the issues we face is that all of these models are very tightly coupled, and there is no easy way to train these models in such a fashion. More generally, we also want to solve the problem of being able to train multi-search task models. Secondly, we also want to make ml4ir a hub for all the commonly used search-based preprocessing tools, so that we have a common NLP tools and tools for unwrapping user positional bias in the click data, and also even tooling for creating synthetic data and labels. On a more ambitious note, we also want to have much more interpretable models for search. Finally, I want to remind you all once again that ml4ir is an open source library for training deep learning models for search. You can do so with limited coding expertise or by endlessly customizing. And more importantly, ml4ir is a shared code base, and we hope it becomes a hub for commonly used search neural network layers, metrics, and loss functions. And ml4ir is built with performance in mind for both the training time and inference time. With that, I want to thank you all for taking the time to attend the talk. And I hope you're interested in going ahead and checking out the ml4ir documentation and installing ml4ir for yourself and taking it for a spin. Thank you.